Everybody can see that, okay? Yeah. Okay, brilliant. Thank you. So welcome to the Introduction to Meta-Analysis training course. So there's going to be two sections to this. The first section I'll present, which is going to be looking at covering a introduction to why we conduct meta-analysis, why it's important, and specifically looking at how we can weight individual studies within a meta-analysis. And then the second session, which Maria is going to cover, is going to be looking at some of the issues that we encounter in meta-analysis, in particular thinking of heterogeneity in meta-analysis, which is very common when you're combining studies, but also talking about some of the bias-related issues, in particular publication bias. And then at the end, we'll finish off with a very quick exercise workshop example, performing meta-analyses and data, which will last for around about 14 minutes. So what is a meta-analysis? Well, a meta-analysis as defined by Glass, famous physician in 1977, he concluded that the best definition was it's a combination of results from a collection of studies which addresses a common scientific question. So there's a number of key elements of this theory as highlighted in red. So the combination of results is obviously very key. Using different types of data and also specifically considering certain types of studies, but also the common scientific question is really key, that we have a specific type of clinical question that might be related to an intervention, or it might be related to a specific type of association that we're interested in looking at. And so it's key that we consider all these different words here. So why do we conduct a meta-analysis? Well, when we have a scientific question in position, we find that in terms of the evidence-based principle, it's much more ideal to synthesize the evidence in a kind of systematic way. So by doing this, we're able to formulate a more structured evidence-based decision-making process. We have a greater idea of the true intervention effect, greater accuracy and precision. And the precision is really key here because when we're pooling across multiple studies, we're essentially getting a much more precise estimate of where the true treatment effect is going to fall within. So we get narrower confidence intervals. There's also a concern of potential bias, prejudice and bias that could occur. So some individual studies might be industry funded and therefore they have a principal bias towards trying to favour a positive finding. So we have to be careful about what types of studies we're including and that we've got a bigger picture of the different types of studies as opposed to those that are industry funded. So if we think of an example, this is an imaginary example called the wonder drug. And it could be, say, a new vaccination that's been developed and it's being rolled out across 5 different centres across the world. And you can see they're all different sample sizes, different recruitment. Now, the mean effect here has been calculated. So this is the mean difference. A higher mean difference displays a more beneficial effect, whereas a mean effect of 0 in this context means there's no difference between the vaccination and the usual, the comparator group. So on first inspection here, what we can see is from the much smaller, so the larger studies who recruited more patients, the mean difference is a lot more conservative. So we've got 0 and 1 in 2 of the larger studies. In some of the much smaller studies, you can see that the mean differences are a lot higher. So there's some concern about how we pool across these studies. Now, one way would be to take a very simple average across the studies, and we can just sum up the mean differences and divide by the total number of studies. And what we end up with is a value of 2. But this doesn't take into consideration the size of the trials. So what we need to do is find a way of how we can assign greater weight to those individual studies that are much larger. So yeah, these two larger studies here, we need to think about how we can assign give more credence to those studies in the pooling mechanism. So alternatively, we can take a weighted average. So here we're looking at the sum of the mean estimates times by the weight over the sum of the weights. And if we go through these calculations, very straightforward, plugging the values in, we end up with now a mean estimate, pooled estimate of 1.2. So it's shifted from 2 to 1.2. So it's much more conservative in estimation. However, when we're pooling across multiple studies, there's always a level of uncertainty which we have to consider in our meta-analysis. So the studies will always be limited in size, and the estimates from them will always vary based on that size, most likely. So there's always a degree of uncertainty. So to reduce uncertainty in an ideal world, we would obviously recruit more patients, have larger studies, larger randomized controlled trials. We'd have more events in the study, so we can look at multiple events, and we'd have a more homogeneous study population that are very similar at baseline. And the conduct and the analysis of the studies will be done to a higher degree. So they've used similar statistical methods to analyze the outcome data, and they've also recruited and randomized patients into the study in a similar fashion. But that's obviously not always the case, and we can't be privy to that being the case. So quantify uncertainty, there are two key statistics we can consider. So the standard error. So in principle, the higher the standard error, this relates to there being more uncertainty. But the key statistic really is the confidence interval. And this is really displays the range of where the true treatment effect lies within. And so in principle, the wider that confidence interval is, this always relates to there being more uncertainty. So I mentioned precision before. To ensure we have precision, we want more narrow confidence intervals, and we can make more informative evidence-based decisions from that. Going back to our wonder drug example, you can see we've got these 5 studies, A to E, very different sample sizes of recruitment, different effect sizes, and we've also calculated the standard errors and the 95% confidence intervals. Now, what you can see from the confidence intervals, clearly, because we're calculating a mean difference here, this means that if the confidence interval includes 0, there's a non-statistically significant effect. And you can see there's only 2 studies that are statistically significant, and that's study C and E. And that's because it doesn't include the value 0. So we've got uncertainty here as well in terms of significance, because we've got 3 of them that are non-significant, 2 of them that are showing a significant result. So one consideration, an idea, is to use the standard error as the weight. So in theory here, what we're saying is that larger trials will have a smaller standard error. This is not always the case, but in most scenarios it is, because they're considered as being more better designs, better recruitment, and baseline characteristics tend to be quite similar, which is a good principle to start a trial. So small standard error means that we assign a larger weight. So if the standard error tends to a small value, if we take the inverse of this, this then tends to a large value. So in principle, what we can use is the inverse of the standard error as the weight, or actually, if we use the 1 over the inverse of the variance, or the inverse variance, this is one way we can assign the weight to the individual studies. So if we go back to our wonder drug example again, and we apply this formula to the data, or user data in this scenario, We're using the sum of the estimates divided by the variance, divided by the total sum of the inverse of the variance. So plugging the values in, we now end up with a pooled estimate of 1.1. So again, it's shifted from 1.2 to 1.1. So it's become even slightly more conservative in estimation. You can also calculate the standard error using this formula here. And then, so we end up with a standard error. If you plug the values in, we end up with 0.3 standard error, pool standard error. So in this example, we've got very different sample sizes, varying results in terms of the effect sizes, different confidence, some significant, some are non-significant. We've calculated the inverse variance weighted meta-analysis mean difference estimate, pooled mean difference estimate is 1.1, and the standard error is 0.3. Now we can calculate the 95% confidence interval, and as you can see, it lies between 0.5 to 1.7. So it's statistically significant, and we've got a much narrower confidence interval from pooling across these 5 studies. We can also display this graphically, which I'm going to show you in a minute. And the graphical representation is what we refer to as a forest plot. So just to briefly explain some of the anatomy of the forest plot. So the square on the forest plots represent the size of the study. So the bigger the square, the more patients are involved in that study. The percentage of the weight, so that's how much we assign the inverse variance weight to that study. And the horizontal line in the plot as well, this represents the confidence interval level for each individual trial. There's also a couple of useful summary statistics which we need to be aware of before we move forward. So when we're dealing with significance, I'm sure anyone who's read clinical papers will be aware of p-value. So obviously, p-value less than 0.05 is determined as being statistically significant. We often hear that uses terms of magnitude. So what's the magnitude in the effect of the treatment effect? Is it an increase, a decrease, a magnitude effect? By what percentage, by what odds ratio or risk ratio, etc.? So this really relates to the effect size, the pooled effect size that you calculated. And precision, as I've mentioned before, really relates to the confidence interval. So how confident are we that our treatment effect is going to lie between a certain range within the confidence interval? So this is a really interesting example, which I know I covered in my PhD, which was looking at a treatment which was put onto the market in 1999, licensed and regulatory approved. It's a drug manufactured by Merck, and it's the Reficoxib Vioxx, which is used mostly as a pain relief drug, as an alternative to naproxen, an anti-steroidal anti-inflammatory drug. And it's particularly used in patients who suffer from arthritis. Now, as time went on, after its approval in 1999, there was a suspected number of cases of heart attacks that had appeared and been reported. So to investigate this, post-marketing surveillance trials were conducted to try and investigate whether this was the case and determine whether or not the drug was safe or not. And it actually led to the drug being withdrawn in 2004. So there is a bit of a case example here. So this is one of the pivotal trials within this meta-analysis that was published, the Bombardier trial in 2000. So this was a year after approval. And what you can see is their individual study results concluded that there was a statistically significantly increased risk of a myocardial infarction event compared to the standard therapy, which is naproxen, in patients taking Reficoxib. And actually it was 5 times higher the risk. And you can see with the confidence interval, because it's not overlapping the null, which is 1, it's statistically significantly worse. Now, is this convincing enough evidence to withdraw the drug at this point based on this individual study? So we'll just think about that, and I'll come back and answer it on the next couple of slides. Here's another study that was published a year later, and this time their results concluded that there was a favorability in showing that reticoxib was worse, 3 times higher, but it wasn't statistically significant. And that's because you can see on the left-hand side, it's overlapping the null, and therefore there is a possibility that it could be better. Sorry, naproxen could be a worse treatment in this scenario. So we've got these 2 trials, one showing a significant increase in myocardial infarctions, and we've got this study showing that there's not a statistically significant increased risk. So based on these 2 individual trials, we don't have enough evidence to withdraw the drug from the market. So what we need is a meta-analysis. So we need to combine all the studies comparing reticoxib with naproxen, randomized control trials, in one simple combined meta-analysis. Okay, and this is what they concluded at the time of withdrawing the drug. So it showed that there was a statistically significant increased risk of myocardial infarction events was when taking reticoxib compared to naproxen, and it was two times higher, 2 times higher risk than naproxen. Yeah, so reticoxib doubles the risk of a myocardial infarction, and this risk, the concept was quite wide, but it's still obviously statistically significant, but it ranges from 30% up to 419% compared to the standard therapy. So now we've got convincing evidence from this meta-analysis because we've got up to 20 studies combined, whereas relying upon the individual trials, the larger pivotal trials, as we went through before, wasn't convincing enough. So this clearly indicates the necessary need for conducting timely post-market surveillance meta-analyses. Now, there is a bit of a cautionary lesson with this example. So many of the trials were actually conducted prior to 2002. And you can see these are all the studies here. This is about 15 trials here, I think. And you can see here, if we conducted the meta-analysis earlier, we can see that there's still a statistically significant increased risk of a myocardial infarction. So in theory, we could have withdrawn this drug from the market a lot earlier, and it was pretty clearly harmful by the year 2001. So we had another 3 years of prescribing this intervention for these patients who we've no account for how many deaths this could have caused. So this really just emphasizes the necessary needs to conduct timely meta-analysis, post-marketing surveillance. And this example is obviously looking at an intervention that can reduce harm and reduce safety. But it's also meta-analysis is very obviously highly used in beneficial aspects of looking at how we can find a beneficial efficacy effect, improve patient condition, improve patient health. But also in a HTA environment nowadays, methodology assessment, a lot of outcomes such as quality of life are being used in a cost effectiveness environment as well to help determine whether a treatment is cost effective and beneficial for the taxpayers and the healthcare system itself in the long run. Okay, so I'll now pass over to Maria to cover some of the issues in meta-analyses. So Maria, I'll share the slides with you now.
Thank you, Alex. I just wanted to say I hope everything was clear so far. I mean, if you've got any questions, you can add in the chat, and we will be discussing them in the end. And I was wondering, Alex, if you can carry on with the sharing, because it's easier instead of me doing it again. So if you can carry on so that I can say like next slide.
Yeah, sure. Okay, when you're ready, Maria.
Yes, I'm ready. Are you sharing?
Apologies.
Okay, so I will be in this part. I will be discussing two key issues in meta-analysis, which are possibilities and opportunities. What meta-analysis gives us compared to a narrative synthesis, but also issues that indicate whether meta-analysis is appropriate and how we can deal with those issues. So there are two key issues. One is around heterogeneity, how we understand it and how we assess it and how we act on it. And the second is around publication bias, what it means, how we assess it, and what we can do. Because, I mean, Alex has already introduced it, but it doesn't mean that applying meta-analysis is going to make your study, your review better. Sometimes if it's not appropriate, it might make it worse. So you only need to apply meta-analysis when is really appropriate. And let's say the main figure that you see every time that you see meta-analysis is obviously a forest plot. And what the forest plot contains is the overall effect, as well as the effects of each individual studies in the forest plot. And from the forest plot, you can tell a lot of things. You can say whether a meta-analysis is actually appropriate or not to some extent. And what we really want ideally in the meta-analysis is that all the values to be very close to the mean. If there is a big variation of each individual study in the forest plot from the main mean, means that there is a lot of variability in the analysis. This is an example, for example, that shows that most of the values, approximately, because if you've got like 40 studies in a meta-analysis, there are going to be variations, but more or less they're all centered around the same mean. And this gives us some confidence that the overall pooled effect reflects more or less what most of the studies have shown. Next slide, Alex. This is another example. This is an example which shows that most of the studies are varying quite a lot. So the values are both positive and negative, and they vary quite a lot from the main mean. And in this case, the overall pooled effect that we have might not entirely reflect what all the different studies show. So what it tells us is that almost like half of the studies they support the let's say the effectiveness of one treatment, the effectiveness of a drug, of sclerotherapy drug in particular, and almost another half they show that it's either non-significant or it can even be negative. So in this case, the pooled effect is really is pulling almost like apples with oranges, and we need to understand why there is so much variation and why our mean doesn't reflect the individual studies. Next. Yes. So if you see more specifically, we've got a couple of studies which show very positive effects. We've got a few studies which show negative effects, and we have a number of studies in yellow which show almost nothing. So we've got a huge variation, and we don't know why this is a variation. It might be really reasonable. It might be because some of the studies they might have used like different dose of a treatment, or they might have used different variation of the treatment, or they might have a different follow-up point. So first, we need to understand whether we actually our pooling makes sense in terms of whether we have the same intervention and the same conditions there, and then we need to understand how we might subgroup them to understand better the treatment effects. But from this forest plot, looks like our pooling at the moment doesn't make sense. We need to understand. We need to find subgroups of studies in order to understand better what's going on with our meta-analysis. Next. So as we said, the key points from those from this forest plot is that that I showed you already, is that different studies always have different treatment effects. The issue is how much variation there is between those treatment effects. If broadly are quite similar, it means that our pooling makes sense. If there is it's a lot of variation, we need to understand the reasons, and the reasons might be several reasons. One reason might be that our meta-analysis in that case is not appropriate. So, for example, someone might decide to pull together all the different pharmacotherapies for depression, but we've got so many different drugs there, so it might not make sense to have all of them together. So we need to make sensible subgroups, or it might mean that we need to also consider whether there is there are some areas that we haven't picked before. So, for example, different follow-ups might show different patterns. If you provide a treatment and you've got a follow-up of post-intervention, might be totally different than looking how the intervention works after 2 years. This heterogeneity, therefore, is really important because it tells us more or less, it guides us to some extent about how our findings look like. Ideally, you would like to predict possible heterogeneity before you start your meta-analysis, and you do that by having some specified, let's say, ideas about additional analysis that you will do. So in your protocol, when you develop it, you might think about how you would assess heterogeneity, first of all, and then how you're going to, after you assess it, how you're going to address it. So in terms of assessing heterogeneity, the good news in meta-analysis is that there are some standardized tests that you can use and find out what is the levels of heterogeneity. And after that, then, after you understand the levels of heterogeneity, you can adapt your analysis as well as conduct additional analysis to address it. So in terms of quantifying it, there are one very common test, next slide, is the I-square test and the Cochrane-Q. The Cochrane-Q test tells you more or less whether you've got heterogeneity in your meta-analysis. Whether is there heterogeneity, yes or no. And you've got a p-value that it also tells you whether this heterogeneity is significant or not. The Hodgkin's I-square test tells you how much heterogeneity you have. So these two statistics have different roles. The first one is tell you whether there is heterogeneity or not, and the second one is to tell you the levels of heterogeneity. Typically, we mostly use HGG, but we also recommend if you can add the Cochrane's Q test as well. And when I say levels, there are actually percentages of heterogeneity. Next slide. So in how we interpret I-square, if you see heterogeneity between 0 to 25%, it's generally low heterogeneity. 25 to 50% is some heterogeneity. 50% to 75% is substantial heterogeneity, and 75%, 100% is really high heterogeneity. And actually, one key issue here to consider is what types of studies you're including in your meta-analysis. If you're including trials and you've got 75 to 100 heterogeneity, this is really concerning because trials are supposed to be the most robust, let's say, study design. So once you pull them together, you wouldn't expect to have as high heterogeneity. If you got over 75, you need to do something about that. It's either that your meta-analysis does not make sense. It's also because you have not considered doing some subgroup analysis. So you definitely need to act if you've got very high heterogeneity, over 75% trials. Now, if you're doing a meta-analysis of observational studies, let's say one factor is associated with another factor. In this case, I-square, it's actually quite sensitive in heterogeneity. Usually, in observational studies, it tends to show almost every time very high heterogeneity. So if everything else makes sense and you're doing a meta-analysis of observational studies and you see very high heterogeneity, you can justify it by saying that it's not as the I-square it's oversensitive with observational studies. But in trials specifically, if you see very high heterogeneity, you need to explore it further, because it indicates that something is problematic in your synthesis. Next slide, please. And as I said, there are different ways of dealing with heterogeneity. One way of dealing with it is adapting the model that you're using for pooling the results. Broadly, there are two different models. The first model is fixed effect model. This means that in your model, you assume no heterogeneity. You assume that more or less your pooled effect is the summary of the individual effects of each study, and this is the fixed effect. The random effect, actually, what it does is that it assigns different weights to different studies based on their quality, based on their sample size, and assuming that there is heterogeneity. In most of the times, we use a random effects model in most cases. But if you see zero heterogeneity, you can still use fixed effects. And there are different reasons why you should use the one over the other. Generally, most of the experts will recommend random heterogeneity if you see between medium to high heterogeneity. If you see very small heterogeneity, you can use fixed effects, but only if there is no heterogeneity or very little heterogeneity. And I'm not going to go in a huge detail about how it is calculated, but there is a statistical logic behind it. Alex knows very well. For example, we actually, in case of having random effects analysis, instead of using one divided by variance in the random effects model, you consider also the heterogeneity. And how we can quantify heterogeneity is more about the sample size. It's more about the quality of the study. So random effects does somehow the job for us. Actually, make sure that the biggest studies and the most robust studies are emphasized more in our pooled effect. If you have already been introduced in systematic reviews, you will see that many people, the introducer will say that not all the studies have the same value in your synthesis. What you need to do is first emphasize the ones that have the greater quality, the biggest ones, and then see whether the rest of the studies agree with, are consistent with the most robust studies. And this is exactly what statistically what the random effect model does. And it highlights in our overall effect the studies that have the biggest sample size and the better quality. So, I mean, there are also different ways of calculating heterogeneity. The most common one is testimonial laid estimate. And you will see that very often when you see the meta-analysis reported in the synthesis approach. Yeah. As I said before, as a recap, let's say, when we consider heterogeneity, the first step for addressing heterogeneity is addressing the way that we calculate the pooled effect. And then we've got two ways of doing that. We've got two ways of pooling our effect. The first is fixed effect, which assumes no heterogeneity in our meta-analysis. The second way, usually the most common one, is random effects. Random effects allow for heterogeneity, emphasize the studies with the highest sample sizes and quality in our analysis. Because the main reason we're doing that is because we want to avoid studies which have really small sample sizes, really big effect sizes as well, strangely big effect sizes, really small sample sizes. So to some extent, if you allow for fixed effects in a study that has high heterogeneity, the studies that are smaller and have really wide confidence intervals, or have really strangely big sample effect sizes, are going to affect very much the overall effect. So let's say that you've got one outlier in your trials, a trial that has not been done properly. If you allow it with a fixed effect, that trial is going to have an important impact in the overall effect. But if you're using random effects, then that study is going to be its impact in the overall effect is going to be reduced significantly. So more or less, it won't have a major impact in the overall effect. Next slide, please. So this is, let's see again now the first forest plot that we've seen once we started with albumin trials. As we said here, in this case, there is very little heterogeneity. Most of the studies are very close to the end, or they are showing more or less similar effects. In this case, the meta-analysis software typically allows you to report both fixed effects model results and the random effects model results. And in this case, because there is no heterogeneity, we find that both of them are the same. And this is what we want in most of the cases. This is an ideal scenario, basically. And however, it doesn't always happen like this. Most of the times, what happens is what we see in this picture. And what we see in this picture is lots of some heterogeneity, actually, not huge heterogeneity. I mean, it's actually large heterogeneity, but when you see the effect sizes, they're still but they're still quite similar. Although what you need to look at most importantly is the confidence intervals. And what we see in the confidence intervals is that if you're using fixed effects, your treatment shows to be significant, mainly because probably has been driven by small study designs. We see no zero within our confidence intervals, and so what our conclusion would be with fixed effects is that sclerotherapy is actually effective, and has a medium effect size, let's say. But what we see if you apply random effect models is that it's actually not effective because it includes zero. So the confidence interval actually ranges from 0.19 to 1.15. So that's important. It's a huge difference if you think about it. So basically, using the one or the other model, you can have totally different conclusions in your meta-analysis. And so, which is the best to use in this case? If you have understood what I was saying, the best model to use is random effects, and the main reason is that you've got 80% heterogeneity. If the heterogeneity was zero, most likely you wouldn't have this difference anyway. But once you see heterogeneity, you need to apply random effects. Otherwise, you might your results might be misleading. Hopefully, in most of the cases, not as misleading as here, that's significant, non-significant, but still can be misleading if you're using the wrong calculation model. Next slide. So this is the extreme one. This is really extreme example. And in this case, to be honest, because there are very few studies, you actually doubt whether you should be doing meta-analysis or not. In this case, might be you should not do a meta-analysis, or you need to understand why one of the trials are so different than the other two. For example, fixed effect shows a significant negative effect, and the random effects show a non-significant but positive effect. So it's really different. In this case, if you have to use a random, definitely again need to use like random effect, but you need to think whether meta-analysis is actually reasonable or not, because because the treatment show completely opposite findings, really. Next slide. I have already discussed about this, but let's say why. If we want to understand why, what are the main causes of heterogeneity, there are two different levels of heterogeneity that we can look at. One is about clinical heterogeneity, it's more about and methodological heterogeneity. Clinical heterogeneity means if you're doing a meta-analysis of drugs, whether there are different doses of drugs, or even the psychosocial treatments, whether you have pulled very different treatments together, like very low intensity treatments with very, very high intensity. In terms of duration as well, issues with the comparator in the treatment. So it's really different to compare your treatment with the usual care, and very different to compare it with another active intervention. So your treatment might be equally effective, but then if your control is actually, if you're providing a very active control, you might not find the difference. It's also about population differences, what populations your treatment is applied, or disease severity. So you need to consider issues around clinical and demographic characteristics of the intervention, the participants there, to understand better the heterogeneity. And you also need to consider methodological issues, such as what was the quality of your studies? Was it how randomization and blinding has been done? What outcomes have been measured? Whether the trials have actually measured the same outcome or used very different measures, and the scales as well. So, but these are important issues to consider, because these issues can actually guide you in doing the second step for addressing heterogeneity. And the second step is doing sensible subgroup or sensitivity analysis. So let's say that you already know that your treatment might have a different effect based on disease severity or based on subgroups of people. And when you're writing your protocol for your systematic reviews and meta-analysis, you will need to consider, you will need to pre-specify a number of subgroup analysis that you're interested in doing. So you might want to compare two different treatments, for example, sub-treatments. So one might be like low intensity or high intensity interventions that use the same principle. Another might be about examining population subgroups, like adults versus older adults, or also in terms of gender. Basically, gender is a bit more difficult, because unless you have individual patient data, you cannot easily do it within the context of aggregate data meta-analysis, as we explained here. But you also may want to do a subgroup analysis on sensitivity analysis, and only include in your analysis studies that have high quality. So, and all these factors usually are determined before your analysis starts. You have a rationale for it. You know how you're going to group the studies together, and then what types of subgroups might be reasonable. And usually it's around clinical heterogeneity and methodological heterogeneity that you check in your subgroup and sensitivity analysis. Next slide, please. Yeah, now, I mean, more or less, as I explained, before you start with your analysis, ask, once you're developing the protocol, have a look at the literature and see what makes sense, what subgroups make sense. You know that you have to do both in terms of methodological. I mean, the main methodological analysis that's always done is around the methodological quality. You know that even before you start, that once you do meta-analysis, you need to do a sensitivity analysis, only on focusing only on studies that have acceptable methodological quality. And this is done by removing the studies with low quality, and you see then what is the pooled effect, and whether the pooled effect of the high quality studies is actually similar with the pooled effect that you had originally. If it's different, then you have to report that and say that basically the methodologically good studies, they have a different pooled effect compared to the studies that the whole pool of the studies. So that's a standard analysis that's always done. But apart from this standard analysis, you can think about clinical differences, intervention differences, patient differences, differences in outcomes. For example, you might have different scales, like you might have 10 trials in your analysis, 7 of them to be using the same scale, 3 of them might be using a different scale. So you might want to compare how they are, how the effects look like across different scales. There are more. Depending on how many studies you have in your review, there might be more advanced things that you can do. You can do things like meta-regression and consider many different factors together, but this is a little more advanced. At this stage, what we really wanted you to understand is heterogeneity is really critical. If there is high heterogeneity, you go for random effects models, and then after that, you also go for a number of sensible, though, based on the evidence and your own judgment before the analysis start, a number of sensible subgroup analysis. One standard subgroup analysis is sensitivity analysis is to take into account the methodological quality of the studies. Other additional analysis can be around clinical characteristics, patient characteristics, anything that is really critical. Another thing that is very important to consider is that this cannot be infinitive. You cannot really cut the cake of the meta-analysis in 100 ways. Basically, you need to have a couple, maybe 2, maybe 3 key subgroup analysis. You cannot do subgroup analysis for everything. They are reasonable, but they have to be pre-specified and only have a limited number, that the ones that make really sense for your analysis. So that's the method. I hope that the discussion about heterogeneity was useful. So the second issue I want to discuss with you is around publication bias. Well, I was just mindful of the time. Can we go one slide back, Alex? I just wanted to show also the forest plot around subgroup analysis. This is how subgroup analysis look like. So in this case, for example, we took into account the risk assessment, the methodological quality of the studies, and we showed, and this is a new forest plot when you split it according to different risk groups, risk assessment groups, and you see very different effects according to the quality of the studies. So what we see is that for studies that are high quality, we see a significant positive effect. Almost 4 times the treatment is almost 4 times better than the control. But when we look at the moderate, the studies with the moderate and low risk, we see we don't see that effect, and actually the low quality studies show almost the opposite effect. And this kind of explains why our findings were so different, because they were driven from low quality studies. So the low quality studies made our conclusions really blurred. But now when we actually split it according to the quality of the studies, we can confidently say that for studies that were really high quality, this sclerotherapy treatment is actually effective. Yes, and let's move to publication bias now. Yes. Well, the issue with publication bias is actually capturing is that some of the studies, there might be studies that might be missing from our analysis, and which we might have excluded, not because we didn't want to include them, but because sometimes they might not be even published. There are different reasons why we couldn't capture those studies. One reason is that they might be unpublished. Next slide. There might be small studies, the ones that have not been published. They might have shown, importantly, they might have shown the negative or non-significant effects. Journals, there is this concept of publication bias, which means that if you show that a treatment is effective, it's more likely that you're going to publish the paper. And the same, if you show any significant effects, it's more likely that journals are interested in publishing it. If you're showing no effect or no significant association, journals may not publish them, or it might also our studies might also have issues around, might be really small to pick to capture the association, might not have enough power, or it might be actually might be lack of enthusiasm. So it's really difficult for someone, especially if they've done a very small study which shows no effect, to sit down writing and pass through all the peer review process that goes into it for publishing. And some of them, they're never really published. Next slide. So what the main problem with publication bias is that because we don't really include all the evidence in our synthesis, this means that our synthesis is a little bit biased. It's biased because we mainly include studies that showed large effects and significant effects. So we don't know whether what we have there then, what we assume as effectiveness, is actually a true effectiveness, or it's just we're actually making this conclusion based on the subset of studies that we have published and are really effective. So to some extent, we might be exaggerating about the effectiveness of one specific treatment or about an association, because we don't really have the full range of studies that we need. And for narrative synthesis, the only way to address this is to look for unpublished studies, to look at the gray literature. Sometimes you can find some of the studies and see whether they show consistent findings with your meta-analysis. Sometimes you won't. But in the good news with meta-analysis is that there is a test that you can do and check whether there is publication bias in your synthesis. You can only do it if you've got at least 8 to 10 studies in your synthesis. So this is the limit. You cannot, if you've got only 3 studies or 4 studies in your meta-analysis, you can test for publication bias. You need to have at least 10 studies, 8 to 10 studies in order to examine it. But if you do have 8 to 10 studies in the same analysis, then you can calculate your publication bias estimates as well as funnel plots. The first thing that we start with for detecting publication bias is by running a funnel plot like this one. In this, what we really want is a very, very symmetric funnel plot that is actually, again, most of the values are clustered together towards the upper stage of our effect. So as we see here, there are in this case the funnel plot is broadly symmetrical. So, but and also many of their values are actually centered together towards the end of the pyramid. Let's see the estimates. Let's go to the next slide, Alex. So what we see in this funnel plot is that there is in our funnel plot there is a gap. So in the red place we see no values. This means that there might be some heterogeneity involved here. I have seen worse cases, to be honest, funnel plots that are completely asymmetrical. But still, in this one, we see that there are not there are values missing from these areas of the funnel plot, which means that there might be some proportion of evidence that we don't really capture in our meta-analysis. Next slide. So what we really need to see is basically no empty areas. So for this, the adaptive and the unadaptive forest plot is really symmetrical, and we see values everywhere. And if we see something like this, more or less, we know that there is not much heterogeneity. If we see a more wide, let's say, funnel plot, and there are areas where you see no values, we suspect that there is significant publication bias. But in addition to just a visual test, there are also there are also statistical tests that we can do. Next slide. Same here. Same, I mean, especially for this for the second analysis for magnesium, again we see a large area of which is empty, which is again means it's quite suspicious. Shows that there is probably public studies that have not been captured in our analysis, have not been published. And we've got two tests that we can do to be sure about it. So we can suspect whether there is heterogeneity or not from the panel plots, but we can also do a statistical test for that. Egger's test is the most common one for capturing publication bias. There are alternatives like the Beck test or the Peters and Harbour test, but most of the times you will see an Egger's test reported in meta-analysis to report publication bias. And this is what we definitely suggest. So if you do a meta-analysis and you've got at least 8 studies in the same analysis, you run for a final plot, you report either as part of your meta-analysis or as part of your appendices, and you also run an Egger's test. Next slide. Yes, I mean, at least, and there you've got several options in terms of how you're doing the meta-analysis. So there is there are statistical softwares like especially Stata is very common for doing meta-analysis, or R is very common as well. You've got Revman, which is linked with the Cochrane collaboration. There is also a comprehensive meta-analysis program, which we have used a number of times. It's particularly helpful when you want when you've got the meta-analysis of observational studies and you want to do some extra calculations of the effect size, because they're not straightforward as in trials. I hope this was helpful as an introduction, and as a summary, then meta-analysis combines studies across estimating the common effect across different studies. So each study has its own effect, and what meta-analysis does is pull them together. There are different ways that this pooling can be done. One is just fixed effect, which is just a summary of what other studies are showing. Random effects, random effects accounts for heterogeneity, and this is what we apply when there is heterogeneity. Publication bias is an important issue. You cannot always do it. You can do it most of the times if you've got more than 8 or 10 studies. And when you report meta-analysis, it's important to be systematic in terms of having a protocol of your pre-specified analysis. You can do subgroup analysis as well to account for heterogeneity, but not infinitively. You have to do only a number, 2, 3, maybe 4, but all of this have to be justified before you start. I hope it was helpful. And now we're going to show you one exercise in Stata about how a meta-analysis can be done. We understand this is very fast track within an hour and a half, but we wanted to give you a flavor of meta-analysis. Alex?
Great, thanks, Maria. Yeah, so I'll just bring up Stata. Find it. So hopefully everybody can see that. So I sent you there's 2 data sets. One is a data set that's going to be looking at evaluating the effectiveness of magnesium to prevent myocardial infarctions. So Maria presented the funnel plot example for this trial. And the second example is looking at the use of BCG vaccinations to prevent tuberculosis infections. So we'll start with the magnesium example first. So anyone who's got access to Stata, feel free to kind of go through this alongside, or if you just want to watch it, that's fine as well. So you open data, which hopefully you get access to. If you go to open, we've got our data set. So we're looking at the magnesium one. If we open this, then the first question is we want to look at the actual data and understand what's going on in there. So what have we got? So we've got the trial name, we've got the trial number, period number, and the period name, and then you've got the key data that is in this quadrant here. So we've got all of the number of myocardial events in the magnesium group, number of non-events in the magnesium group, and then the total number of patients randomized in each of the trials to magnesium. And the same for the control arm as well. And we've also calculated the relative risk of the intervention compared to control with the corresponding 95% confidence interval. The first question in the Word document I sent you is looking at the size of the studies. So what's unique about the difference in the size of studies? Well, we've got these two individual pivotal trials here, the Limit 2 and the SPCR studies, which recruited a much greater significant number of patients. These are kind of outliers in terms of the other smaller trials. So that's the first inspection. And then there's also a question about how they've been published. So this is related to the periods. So you can see that they've published, they've coded these smaller trials prior to the much more pivotal trials. So you can see pre-Limit 2 and then pre-ISIS-4. And it also asks you about the relative risks. Well, you can see that the relative risks are quite varied. You've got some that have got statistically significant increased risk of myocardial infarction, like this one here, which is the BIRD-SCAT study with a relative risk of 2.44. And this one as well, the FELSTED study, which is 1.23. Then you've got most of these studies that are actually below 1. And there's quite a lot of variation there, so we can't really conclude too much from that, which is why we need to conduct a meta-analysis. So going back to our console, if we open up our D file, now you can copy and paste some of the syntax code from the Word document that I sent you. I've just compiled it all into one D file for the ease of use. So initially, you'll need to install all these packages. These are the ones that are relevant we're going to use in this session. Okay. Now, the first question it asks us, it says, if we run a fixed effects meta-analysis, what do we conclude from the data? So we can do this using the meta commands, and we have to organize the data in a very structured way, which is the number of events on the intervention, and then the number of non-events, and then you have the control arm data as well. Then the syntax for the size is the relative risk, and then we've got the pooling mechanism, which we're going to firstly look at the fixed effects. So if we run that bit of code, there we go, and it should give us a forest plot hopefully soon. Just run it again. Oh, there we go. Okay, right. So the first question is, what do you conclude from this running a fixed effect, inverse variance, fixed effects, pooled meta-analysis? So what you can see, the pooled effects is this one at the bottom, the 1.02 with a 95% confidence interval of 0.96 and 1.08. And you'll notice on that this does include 0, so it's overlapping the null, which suggests that it's non-statistically significant. But interestingly, as Maria's spoken about heterogeneity, we've got a high level of heterogeneity here with an I-squared value of 64%. So fixed effects is not the suitable method to use in this scenario. So this is why we need to consider rerunning the analysis using random effects. So you can see here we just need to change the syntax to random I. So if we rerun that again, wait for the forest plot. Now you can see, interestingly, field effects as demonstrated with diamond here. You can see that it's now shifted to a statistically significant effect status. And you can see there that there's a reduction in the risk of a myocardial infarction event. So this is the correct statistic using a random effect, and the DL here represents the Dursamin and Laird estimation, which Maria briefly touched on. So this is the kind of the gold standard method in random effects, and it's always the kind of default method in most software that you use will always revert back to using the Dursamin Laird estimation. So that's the question in this spreadsheet. Asks you, how does it change? Well, we've now shown that there's a statistically significant reduction in the risk of using myocardial infarction, events due to taking the intervention magnesium. Now, there are different summary estimates which you may need to consider. Sometimes some studies may report their summary measures as odds ratio. Although I think in this context, because we're looking at a reduction risk in myocardial infarction events, the relative risk is more suited. There are some statistical properties. Whilst relative risk odds ratios tend to perform very similar, when there's quite rare events, which in this case there may be for things like myocardial side effects, odds ratio does have slightly better statistical properties. And so you can actually notice this when you run it in the odds ratio estimate. You can see that the confidence interval is much narrower than when you run it using a relative risk. However, in this context, it would be reported more as a sensitivity analysis. Another useful measure is the risk difference. So this is more of a kind of a clinical relevance measure that we can use for looking at the absolute change in risk. So if we run this, and that's because it's mostly between a range of -1 and +1, so you can interpret it as a percentage reduction. So if clinicians tend to prefer more. You can see in this example, this is the risk difference, and we can see there's a statistical reduction of -0.04. So we can see there's a reduction of 4% in the risk of myocardial infarction when taking the intervention in this case. Now, we can also look at publication bias through the funnel plot. So it asks us to run the funnel plot, so we can use the meta funnel command. So we set it up in the way that we have the relative risk estimate and we have the confidence interval up and lower limits. And we use the CI confidence interval at the end. So if we run this, it should hopefully give us a funnel plot. And we saw this on one of the slides before, where we had a circle over in this section here where there's lots of missing studies. So on first inspection, what we can suggest from this, we can't conclude yet, but we can suggest that there is clear evidence of publication bias because it's not symmetrical around the centre line. And all the studies tend to be over here on the left-hand side. So they're showing a favourable reduction in the risk of a myocardial infarction, which could suggest we're missing some studies over here, negative results. So we can investigate this further using the regression-based publication bias tests, the Eggers and Begg and Hobart tests. So if we run the Eggers test, so there's a specific parameterization that we need to use here. So we can use the meta bias function command, and we need to orientate the data in the same way as we did with the metham analysis, and then we're using the statistical test at the end. So if we run that, that will hopefully give us the statistics. So there's quite a lot of data here, quite a lot of stats that may be confusing to some folk. But the key statistic that we're really interested in for this test is this section here, which is the p-value of there being any potential bias. And as anybody should hopefully be aware when we interpret p-values, anything that's less than 0.05 indicates that they're statistical significance. You can also actually look at the coefficient and the confidence interval. And obviously you can see from that it's not overlapping the null, so there's a statistical significance there as well. So there's two other tests. Begg's test, which is very similar in performance. I would recommend Eggers. Although the Peter Hobart test actually can be useful when you've got rare events and things like adverse events. So we can check against that, which we have in this case, we've got myocardial infarction. But what you can see is giving us the same result with a statistical significant p-value less than 0.01. Okay, so that's the investigation of publication bias. Now, what we're interested in looking at is a subgroup analysis to explore the potential causes of heterogeneity, because we've got a high level of a high I-squared value. Now, we've included that variable by the period. Remember, this was the smaller trials that were published before the larger two studies, the limit trial and the ISIS study as well. So what we can do is we can do a subgroup analysis based on the period. So again, we're using the metan command here, but we need to introduce this by-product variable, which needs to be included in brackets. So if we run that, it should hopefully give us a forest plot subgroup analysis in the forest plot. So as you can see here, it's separated into the four groups before the limit trial. The limit trial separate on its own, the before ISIS-4 study and the ISIS trial on its own. So what can we conclude from this? So if we look at the pooled effects, we can see that there is a statistical significant reduction in risk in all three of the initial groups up until we get to this large study at the end, the ISIS-4 study. So that would conclude that this trial is having some impact on maybe reducing the performance of the intervention. Okay. Now the next part asks us to look specifically at different time points. So we can actually cut the data at using this if statement in Stata, and we can look at the different time periods and rerun the meta-analysis based on that. So it basically excludes any of the trials post these different time periods. And so you can look at these individually and test for yourself. Yeah, so you can see if we look at time period 3, we can see that there is a statistical significant reduction. If we look at those at time period 2, there's still a statistical significant reduction. I think it's this one that shows there isn't. Let's look. Period 4, yes, there's still a statistically significant. So essentially, that was similar to what we showed in the subgroup analysis, where all of the different groups were statistically significant, other than the major trial at the end, the pivotal trial. Now, what you can also do is you can obviously plot your funnel plots for these different time periods. Again, introducing this if statement. So just let's say, for instance, we want to look at those at time period 3. If we run that the code, it will give us, obviously you can see here we've got less studies, but there still looks to be potentially potentially evidence of publication bias. Now there is a bit of a concern here because, as Maria suggested, ideally we need to have 10 studies to run a publication bias assessment. So I would be wary of this here, and would be probably advised not to report these findings from this publication bias estimation. Now, there is one final additional consideration is to look at the cumulative meta-analysis. Now, I don't think these are particularly beneficial, but what it's essentially doing is the cumulative meta-analysis is it's adding individual trials as you go along. So it can be useful for when you're looking at trials over a period of time. So there might be like a 20-year period, and you want to add in the early trials and then see how that goes on as time goes on, and to the latter, the trials that are published at the later stage. So it might be a context where you see some association changes between, well-being of somebody against certain outcomes of interest like anxiety or depression. And also in this context, we're interested in looking at whether or not the actual treatment effect changes. So if we run this using meta cumulative function, what we can see is that we've got quite a varying bits of results as you keep adding individual studies. So the cumulative effect size changes as time goes on. And they've asked a couple of questions, I think. So how many trials are needed before there's a statistical significant result is obtained? Well, quite simple, because the first trial is not significant, and if we add the second trial, it becomes statistically significant. So the answer to that is just 2. And we're also asking about the impact of the large pivotal trial. So if you remember, this is the limit study, which is the study 8, and the ICE study, which is the study 15. So you can see here that actually this study is actually dragging the effect into slightly less statistically significant effects. And that's the same actually with the study 15 at the end. It's kind of shifted the effect size to a slightly more modest relative risk estimates. We can also compare this to the fixed effect. If we run that, see how that shows. Now you can see there is actually some differences here, and the most obvious one is you can see the large pivotal study, the limit study. There's a big shift actually to the null, and actually study 15 shifts the effect size to a complete new. And that's because, as Marita has pointed out earlier, fixed effect places higher weight on those studies that are larger and have larger numbers of patients. So it tends to follow those studies in terms of the pooling mechanism. So that's the magnesium example. So the second example is looking at the use of BCG vaccinations in patients that trying to reduce patients from getting tuberculosis infection. So let's open the data set for this. We go. So we can browse the data. And what you can see here is we've actually got no names for the trials, unfortunately. But we've got the number of events, non-events, same as before, relative risk, 95% confidence intervals. We've also transformed the data to the log scale and Solera log. I'll get to this a bit later when we run regressions because it's important for that. And we've got this variable as well for latitude. This is the two variables, the continuous variable, which is latitude and where it is in terms of global perspective. And then there's the subgroup, the categorized variable based on higher latitude countries against those that are lower latitude. So the higher latitude countries really relate to those that are mostly European and US based studies, whereas the lower latitude countries are sub-Saharan African countries, so potentially lower middle income countries. So first investigation, we want to run a meta-analysis. So going back to our code. So if we run fixed effects meta-analysis first, what do we conclude? We can see that there is a statistically significant reduction in tuberculosis with use of BCG vaccinations. However, there is a high level of heterogeneity using fixed effects. So we need to switch to random effect to try to account for that heterogeneity. Okay, so if we run the analysis using random effect, again, we can see there is a statistically significant reduction, and the I-squared is still high. But what we can see is there is a slight shift, a bigger reduction, sorry, in the random effects estimate compared to the fixed effects estimate. So that's potentially quite important from a policy perspective. Now, the investigation that we want to carry out next is looking at the subgroup analysis based on the latitudes of the countries. So we can do this again by using the by syntax code within brackets using the variable name. So we can run that and see what it gives us. So we've got these two groups, the high latitude groups. Remember, these are European, UK-based countries. And then we've got the low latitude countries, mostly sub-Saharan African countries. And then, interestingly, here now you can see there is quite a significant difference in the findings. We've seen a big reduction in tuberculosis infection in high latitude countries, but we've seen a reduction in low latitude countries, but it's not statistically significant, and that's because the upper confidence interval limit is overlapping with 1. That's a really key finding for this analysis. Now, what we also ask for, is there any statistical significant differences between the groups? Well, you can do this in 2 ways. Statistically, a better way is to calculate what's called a ratio of the relative risks, which is a bit more statistically complicated. So, and the other way is just to eyeball the 95% confidence intervals for each of the groups. So you can see for the high latitude, it's ranging from 0.2 to 0.44. And if we compare that to the low latitude, 0.58 to 1, these two statistics are not overlapping. So that would suggest that there is a statistical significant difference between the two groups of latitude countries. And you can also compare this in this Cochrane Q statistic as well. If you go down to the between section and read across to the p-value, you can see the p-value is less than 0.05, so that shows there is a significant difference. So as a final investigation, in fact, before we get to the method regression, you can also, again, look at this using the threshold statistic. So if you want to look at countries that are in latitudes below 55 degrees, we could look at that if you wanted to, and you can explore different values, however you see things fit. So to look at the ones that are less than 25 degrees, so you can see there's no statistical significant evidence here to show that there is any difference, any significant reduction in the risk of tuberculosis infection here. So you need to be, I think, I can't remember the specific studies in this example, but it may be dependent upon country by country basis how they perform. Now, latitude is based on a continuous variable. We've got lots of different degrees values. Rather than trying to separate it into a subgroup, we can also analyze it through a meta-regression. The best way to do this is obviously transforming the data to a log scale, which we've done for you, where we have the log relative risk estimates and the standard error of the log relative risk. The reason why we do it on a log scale is simply because it's more of a negative infinity to infinity scale, and it makes it a lot easier in a clinical perspective to interpret the magnitude of change on the scale of any meta-analyses. So we're using a meta-regression function, and we need to include the log relative risk, the latitude variable, continuous variable, and we've also got this function, the WSSE function, which essentially informed data that we're using the standard error of the log relative risk. And this E-form function is just an exponentiation function. So because we're dealing on a log scale, to get back to the probabilistic scale, we need to exponentiate that value using this function here. And then we can graph this method regression as well. If we run the code, so I'll leave the plot for now and I'll get back to it in a minute. But the key statistic, again, there's a lot of data in here. I won't go through all of it, but the key statistic that we're after is the p-value for the variable latitude. And what you can see is, because the p-value is less than 0.05, this means that there is a statistically significant relationship in a reduction of the relative risk as the latitude increases. And you can see that from the plots as well. This is what we call a bubble plot or a scatter plot. Lots of different variations in the name tag. But what you can see is essentially these bubbles represent the individual, the weight of the studies, how many patients are within them. And on the y-axis, we've got the log of the relative risk. So there's a reduction going on there as the latitude increases. So remember, the higher latitude of those countries in mostly high-income countries. So there's a negative linear relationship, which is it's drawn by this line of benefit in red. So what we often conclude, some people may ask, well, what does this study over here mean, given that it's not on the line of benefit? Well, this gives us an idea of how much this study has regressed on the line of benefit or regressed on the line of the mean of the effect size. Sometimes you can publish these graphs in your study. Other times they often don't provide them. So I think in reality you don't have to present them. So that's example of the two data sets. And that concludes the session. So we're very happy to take any questions if anyone's got any. I'll just stop sharing.
There are a number of questions in the chat, Alex. Well, I mean, the first one is assuming availability of the data for Ben, whether carrying out an IPD meta-analysis is sensible. Well, IPD meta-analysis is always great if you've got access to data. What is the main benefit is that with IPD, you will be able to standardize all the scales and make sure that all the methodological issues, most of the methodological issues are resolved. And typically you've got less heterogeneity in your IPD data set. And also you can standardize all the scales with the same way. So sometimes different trials use different types of analysis. You can use the same type of analysis. You can do multiple imputation to account for missing data. There are several advantages. And one of the additional advantages is that you can also control for patient level factors. One of the limitations in aggregate data meta-analysis is that we can look at study level differences. So for example, we can compare different types of interventions, but it's very difficult to control for patient factors, let's say age, gender, other factors that may be reported. But with IPD, you are very well placed to do this analysis. And so it is advisable, just it's a lot of resource consuming. It's difficult it's much more than you might think. I mean, if you've got access to data sets, it's great, but making sure that everyone is going to share their data set, cleaning the data sets and everything takes a lot of time. It's resource intensive. But if you've got the funds and you've got the access to the data, it's definitely much more robust than the aggregate data meta-analysis.
Yeah, I'd agree with that, Maria. I'd follow on. So I think, there's a big resource effort to conduct IPD meta-analysis. Getting hold of the data tends to be the biggest issue. But if you can get hold of the data, then it does lead to a more robust analysis and reduces any of the potential heterogeneity that you might have in your meta-analysis. There are other options nowadays with sneaky, nice convenient work stats packages that can combine both IPD with aggregate level data. But again, there's an associated issue of bias and weighting that has to take place with that kind of analysis. So it's a bit more complicated, really.
Jude's asked whether we haven't run a Q test. Well, you can run a Q test. Usually, I mean, most of the times they're not really required in the let's say in reporting the meta-analysis. What they really need is more or less your I statistic. So in the state example that we had, we did include a test for Q for a Cochrane Q test. We will add it.
Yeah, actually, that's if you look in the Stata console, Judith, just below the pooled results, it does have the Q test within there.
Great.
So it is present. So you've got the Q test and the I-squared statistic in the same table results. It's just it doesn't present it in the forest plot itself. I think there is a way of including in the forest plot, although I'm not that familiar with Stata syntax, so I'd have to look at the help command to do that. So
you've got them in the tables. If you want to add them, definitely in the forest plot. I mean, I wouldn't add in the forest plot. The main reason is that it becomes very busy. Basically, what you need is to report them in the text. You definitely need I square for the forest plot, but having both, it just gets a bit complicated with all the different p-values and everything. So someone who's reading your forest plot, it's easy to get confused. So what I would do is, if you want to report a heterogeneity statistic, report the I-square in the forest plot, and if you want the Q test as well, you report it instead in the actual text or tables. We missed a couple of things, Alex. We missed around the font size. You will have all the data yourself. So basically, you have all the codes. We'll send you the code so that you can rerun the analysis. Probably we should have zoomed a little more so people could see all the details, but we didn't see that comment.
There is a new message which asking about your thoughts, including multiple effect sizes from the same study.
What is?
Yeah,
bottom.
it's the question by Lauren.
Yes. Yeah.
Yeah. So that's can be plausible. So there may be situations where a randomized control trial might have two interventions that are very similar, and they're compared to a placebo or a usual care, and you want to include both of those estimates in. There's two principles you can do. The first one, most likely, is you can pool across those treatment arms and combine it into one entry. So you've just got both the intervention groups combined into one group compared to the usual care, but you have to avoid double counting of the control arm, otherwise it kind of biases the results. The alternative is, if they're slightly different interventions, you can include them both in separately. So you've got two entries for that study. You maybe just need to reference them slightly differently in terms of the intervention, and then pool them in the same way as you would with the meta-analysis examples we've shown you.
As Alex said, I mean, there are two different issues there. Well, if you've got two active interventions in the same control and you want to include them in the same analysis, exactly pull them together, you actually have the control and you can use it. If you've got three active treatments and a control, you have to divide your control by three times, and you can include all of them. But if you want to include two different outcomes in the same analysis, then you cannot do that. So basically, if you've got subgroups and interventions, you can include them in the same analysis, making sure that you reduce the sample of your control arm. The times are equivalent to the number of controls that you have. So if you've got number of interventions that you have, so if you've got two interventions, you have to halve it. If you've got three interventions, you have to divide it by 3. But definitely you cannot include two outcomes from the same exact intervention. So let's say having two outcomes of depression and adding them twice. You have to select one basically, and have a rationale for that. Usually it's like it's the most common measure, or is the most common, is the most well-reported outcome, but not adding in terms of outcomes. Interventions, yes, by halving the control. There is anything else? Just a moment. I see another point, Alex, about Ben is asking how we can determine from an asymmetrical forest plot whether this actually publication bias or reflects genuine math effect of the exposure variable.
I find the question.
2:23 to 2:32. Sorry, the time is 2:32. Ben sent a question, yeah, in the middle, further up.
Yeah, so I mean, the funnel plot really is just used as a form of kind of exploratory investigating whether there might be possible causes of publication bias based on, as Maria showed you, the axis of the effect size, which is on the x-axis, graphed against the standard error of the study. So the more sort of statistical principal way of how we determine publication bias is to calculate the Eggers test is the most common method. And so that would conclude and determine whether or not there's any evidence of publication. I think one of the points you might be trying to get to is if there's a strong association, like a positive association or negative association in the studies. Yeah, that becomes quite difficult, and there are more kind of sophisticated publication bias tests that we can employ for that. So things like trim and fill, where there's imputed missing studies, and it tries to look at whether or not there's a possibility that some of those smaller studies that we may have missed might have had an impact. So these are kind of more useful in sensitivity type analysis in a publication bias environment. Yeah, it's very much, publication bias is very much an area that still needs a lot of work, and there's still a lot of investigations about new methods that could be deployed and how can we more accurately kind of estimate potentially for missing data. So it's a difficult one really to kind of answer really in that sense.
Yeah, I mean, it depends on how much advanced is that question. If you're asking as a beginner why you actually whether you can determine the levels of heterogeneity by the forest plot, by the funnel plot, is basically the reason why we actually include funnel plot. This as a start, as an explorative analysis. We don't make any conclusions based on that, but most of the times you can say if it is highly unsymmetrical that there is heterogeneity there. Many times, because it might be marginal, you will need to run the test. If you want to add to do more sophisticated things around publication bias, as Alex said, there are additional tests that you can impute missing studies and see what happens. But this is a bit more methodological, I would say, question.
I think there's someone Laura has raised their hand. A question there, or?
Hi, yeah, thank you. Sorry, I realise it's past past, so I'll try and be quick. I did actually have something to add to my question, so I should have given a bit more context. I'm working on a meta-analysis that's looking at risk factors for self-harm. So we've got a number of studies where they have, like effect sizes for multiple exposures, and it's the same participants. And yeah, I wondered your thoughts on kind of including multiple effect sizes in that case, where it's like the same participants that have been in each of those analyses.
Maria, as the expert in self-harm, do you want to answer that one?
So Lauren, tell me again, so you've got basically, is it the same analysis, or you're doing multiple analysis on different time points?
No, so basically we're looking at risk factors for self-harm. So we've got, for example, we're going to look at like depression as one sort of category of risk factor, and then some studies have multiple analyses they've done that are relevant to that depression category. So they meet kind of all of our criteria and could all kind of reasonably be included. So there's no sort of obvious choice. So yeah, I just wondered your thoughts on whether, you know, there's a way to like include more than one, or yeah, sorry.
What you're looking is that multiple risk factors that might lead to, let's say, to self-harm or that's totally fine. You don't add them in the same analysis. What you do is different subgroup analysis of different factors, and that's totally acceptable. So I guess you will have one risk factor like depression from one study, and you're going to pull it with another study which shows the same risk factor. It's not like you pulling them together. The problem is when you're pulling them in the same analysis, and it wouldn't be reasonable to pull them because you might have factors like depression, you might have factors like trauma, you might have factor issues like demographic. All you can do the analysis, but separately. So I guess for each of your risk factors, you will have a pooled effect size. Not all of them will be pulled together, so that's acceptable.
Okay, so they would just have to go in separate ones. There's no way to kind of. I mean, sorry.
You can have them in the same forest plot, but you won't have the end point because it doesn't make sense. It doesn't make sense to pull together the gender with depression or gender with trauma. So you will have an overall, let's say, forest plot with different factors that might be leading to self-harm, but pulling them according to the type of stress or the type of factor rather than all the different factors together.
That's what we're sort of planning on doing. I guess it's more where we've got cases, where it's like multiple things in the depression category, for example, reported by the same paper. So it's the same participants in each of the analyses we could include. I read something which was suggesting you could, kind of pool the effect size of the ones within that paper, and then that goes in the meta-analysis. I just wondered if you'd come across this.
We have done that. It's a little bit let's say gray line. Some people accept it, some they don't. I mean, basically we have done it. We have used this approach because we had, let's say, we have done analysis around burnout, for example, which had like different subscales, but some of the studies did not report the overall effect. So we actually we did it. We used the fixed effect across, and we used fixed effects because it's the same participants. So, but you have to explain the methods, and it's an issue of whether most of the will accept it. Some of them will raise some concerns, but it is something that is reasonable unless you go item by item. It's not, if you go item by item, it's going to be really difficult. But if you've got like 2-3 subscales that you want to merge together, that's fine.
Okay, that's great. Thank you. So I realize it's quite a specific question, but that's helpful. Thank you.
Right, so I think let's close the session, and thank you so much, Alex and Maria, for a really interesting session, and some people really enjoyed it. So thank you for attending, everyone. So I'm going to send a feedback form. Hopefully you can give us some comments, feedbacks, and so okay, have a good weekend, everyone.